In 2012, a drill descending more than 3,700 meters through ice at Antarctica nearly contaminated a subglacial lake that had been sealed off for at least 15 million years. This is the life story of what humanity went looking for beneath that ice sand. What it meant to finally touch something that had lived in total isolation longer than our species has existed. It began as a problem of absence. The surface of Antarctica is one of the driest places on Earth, yet satellites hinted at vast bodies of liquid water trapped far below. The question was not just whether water existed, but what it might contain: chemistry, climate records, perhaps life itself. The parents of this search were not a single nation or institution, but a convergence. Glaciology, astrobiology, Cold War era, exploration habits, and modern climate science. A lesser-known fact is that early radar surveys in the 1970s misinterpreted some subglacial signals as rock formations rather than liquid water, delaying focused exploration by years. By the late 20th century, the idea of subglacial lakes had hardened into doctrine. Scientists were no longer asking if they existed, but how many there were and how they behaved. Lake Vostok became the centerpiece of a vast body of water buried beneath nearly 4 kilometers of ice. Discovered indirectly through radar reflection patterns and seismic data, the scale was staggering, roughly 250 kilometers long, comparable in size to Lake Ontario. A lesser-known fact is that pressure estimates suggested the lake remained liquid not just because of geothermal heat, but due to the immense weight of ice, lowering the freezing point of water. The first real decisions of this life story were cautious. Drilling into such a lake risked contaminating an untouched ecosystem, and by extension, corrupting the very data scientists hoped to collect. Competing methods emerged: mechanical drilling, hot water drilling, and clean access systems designed to minimize biological intrusion. A lesser-known fact is that early Russian drilling efforts used kerosene-based drilling fluid, which later became a major concern for contamination protocols. Childhood, in this story, was defined by hesitation and failure. Attempts to reach Lake Vostok began in the 1990s, but repeatedly stalled. Equipment froze. Drill bits jammed. Funding wavered. The environment was not just hostile, was indifferent, applying pressure, cold, and isolation without variation. A lesser-known fact is that drilling equipment had to operate at temperatures below 50 degrees Celsius, where standard lubricants fail and metal becomes brittle. Training, if it could be called that, involved learning how to work in one of the most logistically isolated places on Earth. Every component had to be flown in or transported over ice. Every mistake cost months, sometimes years. A lesser-known fact is that supply convoys to inland Antarctic stations can take weeks to traverse distances that would take hours under normal conditions. Due to crevasse fields and weather delays, early misunderstandings shaped the effort. Some researchers initially believed subglacial lakes were static, sealed systems. Later evidence showed they were dynamic, connected through channels beneath the ice sheet. Water flowed slowly between them, redistributing pressure and heat. A lesser-known fact is that satellite altimetry revealed subtle rises and falls in ice surface elevation, indicating movement of water beneath, effectively mapping hidden lakes without direct access. Small changes mattered more than grand designs. Improvements in sterilization protocols, for example, became central. Clean drilling technologies evolved, borrowing techniques from space exploration. The idea was simple: treat these lakes as if they were extraterrestrial environments. A lesser-known fact is that NASA funded some Antarctic drilling research, specifically to test technologies for future missions to icy moons like Europa. Growth came not through speed, but through refinement. By the 2000s, dozens of subglacial lakes had been identified. International teams coordinated efforts, sharing data and methods. The system around the search matured to logistics, funding frameworks, Environmental treaties. A lesser-known fact is that the Antarctic Treaty System includes strict environmental protections that directly influenced how drilling projects were designed and approved. Standardization followed. Drilling rigs were modified for polar conditions. Sampling equipment was redesigned to operate under high pressure and extreme cold. Even the clothing and living arrangements of researchers became part of the system, optimized for long duration. Isolation. A lesser-known fact is that psychological screening became a routine part of selected Antarctic research personnel. Due to the effects of isolation and confinement, logistics became a science of its own. Fuel, food, spare parts, everything had to be calculated with precision. There was no quick resupply. A broken component could end a season's work. A lesser-known fact is that some Antarctic stations recycle nearly all water, including wastewater, to reduce the need for resupply. By 2012, the effort reached a kind of peak. Russian scientists announced that they had finally penetrated Lake Vostok. The moment was not dramatic in the conventional sense, no sudden discovery, no immediate revelation of life, but it marked a threshold. Humanity had touched a sealed world. A lesser-known fact is that initial samples were not directly from the lake water, but from refrozen water that had entered the borehole and solidified. Other projects followed. The British attempt to drill into Lake Ellsworth faced technical failure when the drilling system could not maintain a clean borehole. Meanwhile, American teams successfully accessed Lake Whillans using hot water drilling, retrieving samples that contained microbial life. A lesser-known fact is that the microbes found in Lake Whillans derive energy not from sunlight, but from chemical reactions involving minerals in the sediment. The defining scenario of this peak was not a battle, but a test of patience and precision. Drilling teams worked around the clock in shifts, monitoring pressure, temperature, and contamination levels. Every step was deliberate. A lesser-known fact is that even the introduction of a single foreign microbe could potentially outcompete native organisms, altering the ecosystem irreversibly. Why did it work? Because the system had matured, technology, protocol, and international cooperation aligned. The lessons of earlier failures were applied. The environment was still hostile, but it was no longer unknown. A lesser-known fact is that real-time data transmission from Antarctic drilling sites is limited, forcing teams to make critical decisions locally rather than relying on remote guidance, but the cost was always present. Human bodies are not designed for Antarctica. Cold stress, isolation, and monotony take their toll. Sleep cycles are disrupted by months of darkness or constant daylight. A lesser-known fact is that vitamin D deficiency is common among Antarctic personnel due to lack of sunlight during winter months. Fatigue accumulates. Decision-making slows. Small errors become more likely. The psychological effect of isolation can be as dangerous as the physical environment. A lesser-known fact is that some Antarctic stations have recorded increased incidents of depression and interpersonal conflict during long winter periods. There are also physical risks: frostbite, hypothermia, and altitude sicknesses. Altitude, because much of Antarctica sits on a high plateau. A lesser-known fact is that the South Pole Station is at an elevation equivalent to over 3,000 meters, affecting oxygen levels and physical performance. And then there is the cost to the environment itself. Even with strict protocols, the act of drilling introduces risk. Contamination, however minimal, cannot be entirely eliminated. A lesser-known fact is that some scientists argue for leaving certain subglacial lakes untouched, preserving them as pristine reference systems. Old age, in this story, is not a decline but a transition. The initial excitement of discovery has given way to a more measured approach. The question is no longer simply what is there, but what does it mean? New technologies, autonomous probes, improved sensors, and remote sampling methods are beginning to replace large-scale drilling operations. A lesser-known fact is that researchers are developing cryobots, robots designed to melt through ice and explore subglacial environments with minimal contamination. At the same time, the focus is shifting. Subglacial lakes are now studied as part of a larger system: Antarctic ice dynamics, climate change, and sea level rise. The hidden water beneath the ice plays a role in how glaciers move and how ice sheets respond to warming temperatures. A lesser-known fact is that subglacial water can act as a lubricant, accelerating the flow of ice toward the ocean. The legacy of this effort is already visible. Techniques developed for Antarctic drilling are being adapted for planetary exploration. The idea of searching for life in extreme, isolated environments has expanded beyond Earth. A lesser-known fact is that missions to moons like Europa and Enceladus are directly informed by what has been learned beneath Antarctic ice. Militaries have learned little directly from this story, but the broader lesson of operating in extreme environments has influenced cold weather logistics and survival strategies. The emphasis on preparation, redundancy, and adaptability is universal. A lesser-known fact is that some Antarctic research has been used to improve equipment for Arctic military operations. What was copied was not the machinery, but the mindset. Careful planning, respect for the environment, and the understanding that some frontiers cannot be rushed. A lesser-known fact is that international cooperation in Antarctica is often cited as a model for peaceful scientific collaboration in other contested regions. And so it ends quietly, not with a final discovery, but with an understanding that some parts of the world, perhaps the universe, require patience more than conquest. Beneath the ice of Antarctica, there are still lakes untouched, systems unmeasured, questions unanswered. The life story of this search is not over, but it has already taught one enduring lesson: that the value of discovery is not just in what is found, but in how carefully we choose to look. In 2007, a satellite pass detected a rise of nearly 3 meters in the ice surface above a buried lake in Antarctica, change caused not by snowfall, but by water moving invisibly beneath kilometers of ice. That was the moment the search beneath Antarctica stopped being about a single lake and became the life story of an entire hidden system, one that behaves more like a slow, pressurized network than a collection of isolated pockets. The idea of isolation had to be abandoned. Subglacial lakes were once imagined as sealed vaults, untouched for millions of years. But data began to show connections channels that allowed water to flow from one basin to another. This reshaped the doctrine of exploration. It was no longer enough to drill into a lake. Scientists needed to understand the pathways between them. A lesser-known fact is that some of these subglacial floods can move billions of cubic meters of water over distances of hundreds of kilometers without any visible surface sign. Birth, in this expanded sense, came from contradiction. Antarctica was supposed to be static, frozen, unchanging. Yet beneath the ice, there was motion, slow, persistent, and powerful. The parents of this realization were satellite technology, improved radar imaging, and a generation of scientists willing to challenge earlier assumptions. A lesser-known fact is that early satellite missions lacked the resolution to detect subtle elevation changes, meaning the dynamic nature of subglacial water remained hidden until the 2000s. The early decisions shifted accordingly. Rather than focusing solely on deep drilling, researchers began to map the entire subglacial hydrological system. Ice penetrating radar became more precise. Computer models grew more sophisticated. A lesser-known fact is that radar signals must be carefully tuned to distinguish between ice, water, and sediment, as each reflects electromagnetic waves differently under extreme pressure conditions. Childhood, in this broader narrative, was a period of recalibration. The tools were improving, but interpretation lagged behind. Data sets conflicted. Some lakes appeared to vanish, only to reappear later. Others seemed to merge. The system was more complex than expected. A lesser-known fact is that some disappearing lakes were actually draining into neighboring basins, redistributing water rather than losing it entirely. Training for this phase was intellectual as much as physical. Scientists had to learn to read indirect signals, subtle shifts in elevation, variations in radar returns, anomalies in ice flow speed. There was no direct observation, only inference. A lesser-known fact is that even a change of a few centimeters in ice surface height can indicate massive water movement below. Due to the scale of the system, early failures were often conceptual. Models that assumed static conditions produced inaccurate predictions. It became clear that time had to be treated as a variable. Lakes filled and drained over years or decades. A lesser-known fact is that some subglacial lakes have complete fill and drain cycles that can take less than 10 years, far faster than originally assumed. Small adjustments made the difference. Incorporating real-time satellite data into models allowed for dynamic tracking. Collaboration between disciplines, glaciology, hydrology, geophysics became essential. A lesser-known fact is that interdisciplinary teams often outperformed specialized groups in predicting subglacial water movement due to the complexity of the system. Growth followed this shift in understanding. The number of known subglacial lakes increased dramatically, from a few dozen to hundreds. Each new discovery added to the map, filling in gaps and revealing patterns. A lesser-known fact is that over 400 subglacial lakes have been identified beneath Antarctica. Though estimates vary as detection methods improved, standardization emerged in data collection and analysis. Satellite missions were calibrated to detect, mimic changes in ice elevation. Ground-based radar surveys were coordinated to cover larger areas systematically. A lesser-known fact is that some satellite instruments can detect elevation changes as small as a few millimeters, enabling highly detailed monitoring of subglacial activity. Logistics evolved alongside knowledge. Field campaigns became more targeted, focusing on key regions where models predicted significant activity. Resources were allocated with greater precision. A lesser-known fact is that deploying a field team to a remote Antarctic site can cost millions of dollars, making efficiency and planning critical. The system around the search matured into a global network. Data was shared across countries and institutions. The Antarctic Treaty Framework facilitated cooperation, ensuring that findings contributed to a collective understanding. A lesser-known fact is that Antarctica is one of the few places on Earth where scientific data is routinely shared internationally without restriction. Peak effectiveness came when observation and modeling aligned. Scientists could predict when and where subglacial lakes would fill or drain, and then confirm those predictions with satellite data. This feedback loop marked a turning point. A lesser-known fact is that successful predictions of subglacial floods have been used to validate climate models, improving their accuracy. A defining scenario involved tracking a series of connected lakes over several years. Water was observed moving sequentially from one basin to another, like a slow-motion cascade beneath the ice. The scale was immense, but the process was almost invisible. A lesser-known fact is that these cascading events can influence the of glaciers above, altering ice flow patterns over large. Why did it work so well at this stage? Because uncertainty had been reduced, not eliminated, but managed. The system was understood well enough to anticipate its behavior. Technology, theory, and observation reinforced each other. A lesser-known fact is that uncertainty in subglacial models is often quantified explicitly, allowing scientists to assign confidence levels to their predictions. But the cost of this knowledge remained significant. The human element did not disappear. Researchers continued to work in extreme conditions, often isolated for months. The mental and physical strain persisted. A lesser-known fact is that communication delays and limited connectivity can exacerbate feelings of isolation among Antarctic teams. There was also a cost and complexity. As understanding grew, so did the realization of how much remained unknown. Each answer raised new questions. The system was not just dynamic, but sensitive to changes in temperature and pressure. A lesser-known fact is that even small increases in basal melting can alter subglacial water flow, with potential implications for ice sheet stability. Environmental concerns continue to shape the work. The risk of contamination, while managed, could never be fully eliminated. Ethical considerations became part of the decision-making process. A lesser-known fact is that some proposed drilling projects have been delayed or canceled due to environmental concerns, despite their scientific value. Old age, in this phase, is marked by integration. The study of subglacial lakes is no longer a niche field, but part of a broader effort to understand Earth's climate system. The focus has shifted from discovery to application. A lesser-known fact is that subglacial water dynamics are now included in models predicting sea level rise, highlighting their global significance. New technologies are beginning to take over. Autonomous systems, remote sensing advancements, and improved computational models are reducing the need for large-scale field operations. The work is becoming more efficient, but also more abstract. A lesser-known fact is that machine learning algorithms are increasingly used to analyze satellite data, identifying patterns that might be missed by human observers. The legacy of this expanded life story is one of perspective. What began as a search for hidden lakes has become a deeper understanding of how ice sheets function. The lessons extend beyond Antarctica, informing studies of glaciers and ice caps worldwide. A lesser-known fact is that similar subglacial systems have been identified in Greenland, suggesting that these processes are not unique to Antarctica. What has been copied is the approach: observe, model, validate, and refine. This iterative process has become a standard in earth science research. A lesser-known fact is that the integration of satellite and ground-based data is now considered a best practice in many fields of environmental science. And so the story continues, quieter, now but no less important. Beneath the ice, water still moves, unseen and largely unmeasured. The system evolves, responding to forces both local and global. The life of this hidden network is ongoing, its rhythm slow but consequential. In the end, the lesson is not about what lies beneath the ice, but about how we learn to see what is hidden. In 2019, a seismic survey suggested that sediment layers beneath parts of Antarctica could be several kilometers thick, deep enough to preserve a continuous environmental record stretching back tens of millions of years. That possibility widened the stakes again, turning the search beneath the ice into something more than a hunt for water or life. It became a slow excavation of Earth's memory, written in pressure, chemistry, and time. The story at this stage no longer belonged to a single lake or even a network. It belonged to the interface between ice, water, and rock, the buried boundary where glaciers meet the continent itself. This was where movement was decided, where friction was reduced or increased, where entire ice sheets could accelerate or stall. A lesser-known fact is that basal sediment saturated with water can reduce friction by more than 90%, effectively allowing glaciers to slide rather than grind forward. Birth, in this phase, came from urgency. Climate models were improving, but they still struggled to predict how quickly ice sheets could respond to warming temperatures. The unknown variable was beneath the ice. Without understanding the conditions at the base temperature, water pressure, sediment composition, predictions remained incomplete. A lesser-known fact is that early climate models often treated the base of ice sheets as static, an assumption now known to introduce significant errors. The parents of this expansion were not just sciences, but dated decades of measurements, reinterpreted with new tools. Airborne radar surveys map vast areas with increasing resolution. Seismic studies revealed layers of sediment and rock. Satellite data tracked changes in ice flow. A lesser-known fact is that seismic waves travel at different speeds through water, ice, and sediment, allowing researchers to infer the composition of the ground without direct sampling. Early decisions reflected caution and ambition in equal measure. Drilling into subglacial lakes had been difficult. Drilling through ice and into sediment beneath them was even more complex. New systems were designed to extract cores without contaminating the environment or disturbing the delicate balance of pressure. A lesser-known fact is that maintaining pressure equilibrium during drilling is critical, as sudden changes can cause water to surge into the borehole or freeze unexpectedly. Childhood was marked by technical limits. Instruments could detect layers, but interpreting them required assumptions. Sediment could be soft or compacted, water-rich or dry, ancient or recently deposited. Each possibility implied a different history. A lesser-known fact is that some subglacial sediments contain microfossils, offering clues to past climates when Antarctica was not fully glaciated. Training shifted toward integration. Geophysicists, glaciologists, and climate scientists had to work together, aligning their methods and models. Data from one field had to make sense in the context of another. A lesser-known fact is that mismatched spatial scales kilometers for satellite data versus centimeters for sediment cores can complicate interpretation, requiring careful calibration. Early failures often came from overconfidence. Models that fit one region failed in another. The Antarctic ice sheet is not uniform. It varies in thickness, temperature, and underlying geology. A lesser-known fact is that parts of East Antarctica sit on ancient, stable cratons, while West Antarctica rests on more geologically active terrain. Influencing subglacial conditions, small changes again proved decisive. Improved resolution in radar imaging revealed finer details. Better algorithms allow for more accurate interpretation of seismic data. Incremental advances built a clearer picture. A lesser-known fact is that advances in signal processing have allowed researchers to detect features as small as tens of meters beneath kilometers of ice stock growth. In this stage was measured in depth rather than breadth. The focus shifted from mapping to understanding. What did these layers mean? How did they interact? How did they influence the movement of ice above? A lesser-known fact is that subglacial sediments can act as both a lubricant and a brake, depending on their composition and water content. Standardization followed, particularly in data collection and modeling. Protocols were established for interpreting radar and seismic data. Shared databases allowed researchers to compare findings across regions. A lesser-known fact is that international collaborations have led to the creation of unified Antarctic data repositories, improving accessibility and consistency. Logistics remained a constant challenge. Accessing remote regions required careful planning. Equipment had to be transported across vast distances, often under extreme conditions. A lesser-known fact is that some field campaigns rely on ski-equipped aircraft to land on unprepared ice surfaces, enabling access to otherwise unreachable areas. The system around the research matured into a layered effort. Surface observations, airborne surveys, and limited drilling all contributed to a comprehensive understanding. Each method had strengths and limitations, but together they formed a coherent picture. A lesser-known fact is that combining multiple data types can reduce uncertainty significantly, as independent measurements can validate each other. Peak effectiveness in this phase came when the pieces aligned. Models incorporating subglacial conditions began to produce more accurate predictions of ice sheet behavior. The influence of hidden water and sediment was no longer speculative. It was quantified. A lesser-known fact is that incorporating subglacial hydrology into models has improved predictions of glacier by measurable margins. A defining scenario involved the study of rapidly moving glaciers in West Antarctica. These ice streams were found to be strongly influenced by conditions at their base. Where water and soft sediment were present, movement accelerated. Where the base was frozen or rough, movement slowed. A lesser-known fact is that some ice streams can move several 100 meters per year, far faster than surrounding ice. Why did it work here? Because the system had reached a level of resolution where cause and effect could be linked. Observations matched predictions. The hidden variables were becoming visible, at least in part. A lesser-known fact is that uncertainty remains high. In some regions, particularly where data coverage is sparse, highlighting the limits of current methods, the cost of this deeper understanding was not just logistical or financial, but cognitive. The more detailed the picture became, the more complex it appeared. Simple explanations gave way to interconnected systems. A lesser-known fact is that increasing model complexity can sometimes reduce interpretability, making it harder to identify. Key drivers, human costs persisted as well. Fieldwork in Antarctica remained demanding, with long hours, harsh conditions, and limited support. The physical and psychological challenges did not diminish with technological advancement. A lesser-known fact is that even experienced researchers can experience polar fatigue, a combination of physical exhaustion and mental strain unique to extreme environments. Environmental costs remained a concern. Drilling into subglacial environments carried risks, and even indirect observation methods had impacts. The balance between discovery and preservation continued to be debated. A lesser-known fact is that some researchers advocate for no-drill zones to protect particularly sensitive or scientifically valuable areas. Old age in this stage is characterized by refinement and restraint. The focus is shifting toward minimizing impact while maximizing information. Remote sensing technologies are becoming more advanced, reducing the need for invasive methods. A lesser-known fact is that next-generation satellites are expected to provide even higher resolution data, potentially revealing new details of subglacial systems. At the same time, the questions are evolving. It is no longer just about what lies beneath the ice, but how it will change in the future. Climate change adds a new layer of urgency. The stability of ice sheets and their contribution to sea level rise depends in part on the hidden systems below. A lesser-known fact is that even small changes in basal conditions can have outsized effects on ice sheet dynamics. The legacy of this phase is one of depth and connection. What was once a hidden world is now partially understood, integrated into broader models of Earth's systems. The knowledge gained has implications far beyond Antarctica. A lesser-known fact is that insights from subglacial research are being applied to studies of other ice-covered regions, including glaciers in mountainous areas. What later designs, scientific and technological, have copied is the layered approach, combining multiple methods, integrating data across scales, and maintaining flexibility in interpretation. This has become a template for studying complex systems. A lesser-known fact is that interdisciplinary approaches are increasingly recognized as essential for addressing large-scale environmental challenges. And so the story settles into a quieter rhythm again. Beneath the ice, the processes continue. Water flows, sediments shift, ice moves. The system is not static, and neither is our understanding of it. The life of what lies beneath Antarctica has not ended. It has simply become more subtle, more intricate, and more difficult to ignore.